All right. So, everybody cool with that? All right, kind of a late start on the video here. All right, so Newton's second law, acceleration is net force over mass, and obviously the variables are acceleration, net force, and mass. We good? Okay. All right. So for this definition to make sense, we need to talk about mass. This is the first time this year we've actually talked about mass, right? Okay. So in chemistry, you guys, I'm guessing, I've never been in your chemistry class, but I'm guessing that mass is defined as a measure of how much matter makes up an object, right? So when you measure mass, what you're doing is you're counting protons, neutrons, and electrons, right? More of those particles means more matter, means more mass, right? Okay? And to be honest, on a conceptual level, that's the definition that I prefer. Okay? And a lot of physics textbooks define mass as a measure of an object's inertia. Okay? Which is great, but then we have to define what inertia is. All right? So here's what inertia is. Inertia is an object's resistance to a change in motion. All right? Inertia is an object's resistance to a change in motion. So imagine that you've got a semi-truck and a skateboard, and they're both sitting at rest, and you want to move them both. And you go and you push them both with the same force. Which one's going to move more? The skateboard, right? So when you apply the same force to the two objects, the object with less inertia will accelerate more, right? In other words, it's less resistant to a change in motion because it has less mass, it has less inertia. Cool? Okay, it's a little meta, right? Okay. So a physics person would say that to find a mass, you apply a known force to it, find its acceleration, and then its inertia tells you sort of what the mass is. Okay? Good? All right, so here's a real simple example of this. Suppose I give you two objects, and I go, hey, which of these two objects is heavier? What do you do when you're trying to decide which one's heavier? You kind of do this, right? Right? You can like bounce them in your hands, right? Think about what you're doing. You're getting them moving at the same rate, and then seeing which one's harder to change the motion of, right? Right? You're causing a change in motion, right? So which one takes more force to change the motion? Which one's more resistant to you changing its motion? That's the one with more mass, the one with more inertia. Cool? Cool. All right. All right. So this is basically more of the same. I copied this one out of the textbook notes. The reason I copied it, I think I liked this example down here at the bottom. But okay, so before I get there, so a couple quick comments. These two definitions are basically what I just told you. I did not emphasize this. This will come up more, I think, in the next batch of notes. Mass and weight are not the same thing. Mass and weight are not the same thing. They're very closely related, but they're not the same thing. All right. Tomorrow we'll learn that weight is the force of gravity on an object. Or I guess we've learned that now. But so gravity pulls stuff down, right? All right. The amount of force that gravity uses to pull something down, that's weight. Okay. In outer space, something is literally weightless, right? Like you're way out in outer space, away from planets and moons and stuff, right? But you still have mass. Okay. When you go to the moon, you still have just as many protons, neutrons, and electrons. You still have the same mass, but your weight is different because the moon is smaller. It has less sort of force of gravitational attraction. Cool? Yes.
How would you mass something in outer space?
You would have to push it with a known force and find the acceleration. Yeah. All right. And you can, I don't know if you guys noticed that he used the word mass as a verb in the same way that you can use weigh. I guess weight and weight. But yeah, you can mass something, and that just means find the mass of it. Okay. All right. And so that ties in closely to this, right? So if you wanted to find the mass in outer space, you would have to find the acceleration for a known force. All right. So here's just a simple example that if you apply 8 newtons, a fixed force of 8 newtons, if you apply that to 1 kilogram, it'll accelerate at 8 meters a second squared, right? Because acceleration is net force over mass, right? 2 kilograms is going to give you half the acceleration, right? Half a kilogram would give you twice the acceleration. Cool? If you go the other way, if you know the acceleration, then you can find the mass. And that's exactly what Patrick just said. Cool? the last thing I'll say, I think that you guys all know this, but so usually when you see Newton's second law in books, usually it's written as either just F equals ma, which is all kinds of wrong. Why is that wrong? Because it doesn't imply net force, right? So really you need net in front of it, or net as a subscript or whatever. I never liked writing it that way, because I remember the first time when I was in whatever 11th or 12th grade, whenever I took physics when I was a kid, or when I was your age, sorry. This always frustrated me because the first time I looked at this equation, I thought that this was telling me that the force was a result of the acceleration, right? Like, oh, I've got this object that's accelerating. That results in a force of whatever. And that's not the way it works. It's the other way around. Okay, I like this equation because it shows us that the acceleration that the object has is dependent on what the net force is and what the mass is. Okay, it's the force that causes the acceleration, not the other way around. So just on sort of a conceptual level, this equation always sort of made more sense than me. Okay, now, mathematically, they're both accurate, right? I mean, do you guys understand that? Like, we're going to use this all the time this year. Okay, so you do need to be familiar with it, but on a conceptual level, I like this better. Cool? Any problems? All right, I'm going through this all super quick, because theoretically, this is stuff you should have gotten last year. Am I going too quick for anybody, or? Okay. All right. Okay, so there's not a whole lot to this one. Oh, gotcha. All right, so you're going to be solving problems like this. So this one says a 10-kilogram box is being pushed across a horizontal surface. So let's draw it. Here's the surface. Here's the box. I always like to write the mass of the object in the box. All right. And it's being pushed across a horizontal surface with a force of 70 newtons. 2 seconds, Alex. So here's our force. Let's give it a name. So maybe it's Roy who's pushing it. We don't know, whatever. 70 newtons. All right. And then the problem tells us that it's accelerating at 3 meters a second squared. And then it says then, ... I want you guys to think about what the then is while I answer Alex's question.
Is kilograms the SI unit for mass?
Yeah, did I not put that in here? Maybe I deleted that page by accident.
It is right next to the equation.
Oh, right, there we go. Thank you. I knew I had it in there somewhere, yeah. Yes. Yeah. No, I'm glad you brought this up, though, because I think then that here's what I didn't end up putting in there. 1 Newton. So when they invented the metric system, they were smart about it. They said, well, let's see. Force, the intent of force is to cause acceleration, right? So we need to come up with a unit with which to measure force. Well, why don't we call our units newtons, because that guy was really smart. All right? And we're going to make 1 Newton of like force unit. We're going to make that equal to the amount of force required to take a 1 kilogram object and accelerate it at 1 meter per second squared. So it's a kilogram meter per second squared. Okay? So that's the definition of a Newton. Right? So as long as you keep your mass in kilograms and your units in newtons, and then all of your accelerations in meters per second squared, then everybody sort of gets along well and everything works out the way we need it to. Follow? So thank you for asking that. That's something that I must have somehow, when I wrote these notes up, I must have deleted it or moved it and then not put it back or something. All right, everybody good? Cool. So this is a definition. And this is a 1, not the word in. All right, good? All right. So where were we? We talked about this, we talked about this, we talked about this. All right, so there's a problem here. This sort of doesn't add up, does it? Because if 70 newtons was my only force, so if my net force is 70 newtons, then my acceleration would be net force over mass, which is 70 newtons divided by 10 kilograms. You don't have to do this, but just to follow up on the previous point, that 70 newtons is 70 kilogram meters a second squared divided by 10 kilograms, and so you'd get 7 meters a second squared. Well, that doesn't jive with what I told you the acceleration was. Right? So there's got to be something wrong here. Right? So, you got an idea there? There's got to be another force. That's the only way this can possibly work, right? Right? So, this concept of acceleration equals net force over mass, and net force equals mass times acceleration, the idea is this. In the problem, there's always going to be enough information for you to either find the acceleration or find the net force. Once you've done that, find the other one. Okay? All right, a couple of you guys have said, how do I solve problems? That's a thing. All right? So what are ways we can find acceleration? Well, you can use the definition. You can use this guy. Oops, sorry. So those are a couple ways you can find the acceleration. You could use that equation to find acceleration, right? And then once you've got your acceleration, you can find the net force, right? Follow? All right, in this one I just gave you the acceleration, so maybe I'm getting ahead of myself. But are we good with that? All right, now net force. There are two ways to find net force. One way is to use Newton's second law. You can just do mass times acceleration, right? What's the other way? What's the definition of net force? Add up all the forces. So if you've got 5 forces, then it's F1 plus F2 plus F3 plus whatever. All of your forces add up, right? All right, a common mistake that I see students make, though, is they'll try to use this equation to find the net force when they're missing a force. And you can't do that, right? If you want to find your net force this way, you have to know all of the forces to add them all up, right? Like if I said, let's total up how much money is in this room, and somebody left the room, then we couldn't do it, right? Because we'd be missing one of our values, right? Cool? All right, so that was a sort of a tangent, but an important one. But these equations are going to be sort of central to all of the problems in this chapter. Questions? Okay, cool. So, let me do this. No, that's not at all what I wanted to happen. This little guy's real little. Okay. Friction. So what should I do? Okay, we can draw it, although in this one it's fairly obvious, but we won't always know that necessarily. So let's pretend for a minute this problem is a little bit more complicated. Mickey, you got an idea? No, come back to you.
After the net force would be given acceleration.
Good, yeah. This acceleration, by Newton's second law, is determined by the net force. So find that net force. So we've got 10 kilograms. We've got 3 meters a second squared. That means the net force is 30 newtons, right? So now most of you are looking and you're going, okay, friction is 40 newtons. Yes, I get it. All right. I started with an easy example because I want you guys to sort of understand sort of how everything all ties together here. All right. I promise you the next example is more involved. All right. Now, when you're finding a missing force, there's really only one way to find a missing force. And the way that you do that is by using the definition of net force. So in this problem, net force is all of my forces added up. So it's the force of Roy plus the force of friction, or whatever the resistive force is. We don't really have a way of knowing specifically that it's friction, but whatever. There's something working against the motion, right? And so now we can find our missing force. Net force is 30. Force of Roy is 70 plus force of friction, and solve, right? What do you get? Good, you get negative 40. What's the significance of the negative? It tells us what direction it's going in. All right, so if you trust the equations, they will keep track of your signs for you. And they'll tell you direction. They'll tell you information about the direction. Cool? Questions? All right, now, technically speaking, I'm missing two forces here. We're not going to worry about force of gravity or normal force yet. That comes up in the next batch of notes. So hold tight on those. Okay, I know that's something you guys all know about, but for now, we're going to not worry about it. All right, so is everybody good? All right, next example. So this, we're ramping up real quick here. So the next example is almost the exact same thing. Oops. The next example is, it's basically the same thing, but now it's vectors. Okay? And other than the fact that it's tedious, because you've got all these components to deal with, conceptually it's the exact same thing. Okay? So, are we ready? Okay. You might, no, I guess I gave you guys a full page. Good. All right, so here we go. Let's do part A. Let me grab my notes. I'm not recalculating stuff that I've already calculated. Well, you were going to say something before. Were you just going to answer the question, or do you have something? Okay. All right, so is everybody good before I go on? All right, so it says, suppose a 2.5 kilogram box of tiny unicorns sits at rest on a frictionless floor. Al, Bob, and Carl are fighting over the box. Al pulls the box with the force of blah, 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 while Bob pulls the box with the force of blah, 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 blah. A, how much force does Carl need to give the box an acceleration of that? So kind of the same idea. We're missing a force, right? Last time we were missing the force of friction. This time we're missing a force of Carl. Good? So here's how you deal with it. First of all, start by making yourself a little drawing. And to be honest, in this problem, I don't know that it really helps you that much, but it's a good habit to get into. All right, so here's my box. This is an overhead view of the box, right? Because my directions are all compass directions, north, south, east, and west. All right, so I'm omitting gravity pulling the box down and the floor holding it up, because those cancel, and because we haven't learned about them yet. Okay, so put in your axes. Here's your y-axis. Here's your x-axis. All right, and then let's identify what we know. So we know that the force of Al is this. 20 newtons at 30 degrees south of east. So force of Al equals 20 newtons. And then I know that this angle here is 30 degrees, right? And then it says Bob pulls the box with a force of 15 newtons at 20 degrees south of west. So kind of off this way. Oops, I guess I should make that force a little shorter, shouldn't I? Force of Bob is 15 newtons, and this angle in here is 20 degrees. Follow? All right, and then we're looking for the force of Carl. What does the force of Carl have to be in order to get, I did too, an acceleration of, I don't know why I just said that, that wasn't even funny. So our acceleration that we want is 5 meters a second squared at 60 degrees south of east. So just draw a little vector. 60 degrees south of east is kind of that way. Notice, my acceleration vector doesn't go on my drawing. It's separate, right? Because it's not a force, right? Right? And then we know that this angle here is 60 degrees. All right, are we all good with that? Okay. So, remember, at the heart of this is Newton's second law. So if you know the net force, find the acceleration. If you know the acceleration, find the net force. Can we do either of those things right now? Yes. So my net force is going to be the mass times the acceleration. Now, here's something that hasn't really come up yet. First of all of these values that I've been talking about are vectors. This force is a vector, it has direction. This force is a vector, it has direction. This acceleration is a vector, it has direction. Mass is a scalar, right? So do you guys remember how you do scalar multiplication? You just multiply all the components, right? But it doesn't change the direction. So what that means is, always, without exception, the direction of your net force is the same as the direction of your acceleration. Okay? Because it's the force that causes the acceleration. The net force that causes the acceleration. Yep. So what I just said was, without exception, the direction of the net force and the direction of the acceleration will always be the same. And the reason for that is the equation here is just scalar multiplication. So you're just sort of making your vector bigger or smaller or whatever, scaling it up or down. All right, how are we doing? Pretty good? All right, so let's find our net force. We know our mass, we know our acceleration, so we can do this. I didn't do the thing that I said that I like to do, which is write the mass in the box. So mass equals 2.5 kilograms. Sorry, that's sloppy. 2.5. Cool. Why I feel like this number is small. Okay, so now I can find my acceleration. So it's going to be 2.5 times 5, right? So 2.5 kilograms times 5 meters a second squared. It's going to give us what? 12.5 newtons at 60 degrees south of east. Everybody good? All right, so at this point, now it's just vector addition. Okay, we know two of our vectors, a plus b plus c, question mark, equals this mass. Cool? So, let's go through vector addition the way that you're supposed to do vector addition. All right? Any questions before I go on? I'm going to free up some space here on the board. So before I do that, I'm going to make sure we're good. Reset? Christian, you okay back there? You got it? Okay. Oh, I got you. Okay, no, I was just asking if you were done writing, but okay. I'll see you tomorrow then, is that right? All right. Notes are recording, and you can get them from somebody else if you want. All right, so here we go. Let's take this mess. Okay, so here's what I want to do. There are three vectors involved in this problem, right? There's force of A, force of B, force of C. Those have to add up to my net force, right? So, what I'm going to do is I'm going to take each of those vectors and write them in unit vector notation instead of in magnitude direction notation. All right? So, for example, Al pulls a box with a force of 20 newtons at 30 degrees south of east. So I'm just going to do my trig, use cosine and sine, and find the components. Good? Repeat the process for B. Repeat the process for the net force. Do I need to write out those calculations, or can I just show you the results of those calculations? That's the result. All right, watch me go. All right, so here we go. So force A, once you break it up into unit vector notation, and again, I kept a lot of extra significant digits. I guess they're technically insignificant digits, so that I can round at the end. All right, so here we go. So it's 17.3205 I minus, it turns out to be exactly 10 J, and this is all in newtons. So that's the force of A. The force of B is negative 14.0954 I minus 5.1303 J newtons. Force of C, we don't know. So I guess we can call this FCX I plus FCYJ. This is a J, if you can't tell. Cool? All right, and then we know our net force because we found it here in green in very small letters. And so that net force ends up being 6.25 I minus 10.825 J newtons. So kind of bookkeeping at this point, right? Pretty good? Okie doke. All right, so now we just gotta, each component, both my x and y components, so this gives me an equation, and this gives me an equation, right? So it's 17 minus 14 plus x equals 6.25, right? Negative 10 minus 5 plus y equals negative 10. Follow? So, do your algebra. FCX ends up being 3.02. I guess the I is redundant because I've said x, but and then your FCY ends up being 4.305 J. These are all still in newtons. So now I can find the force, right? So just draw it. Let's see. Force of Carl in the x direction is 3.02 newtons. Force of Carl in the y direction is 4.305 newtons. We're looking for the force of Carl. So Pythagorean theorem, a little bit of trig. And the force of Carl ends up being 5.26 newtons at 54.9 degrees. What? Let's see, if it's pointing this way, that's going to be north of east, right? Make sense? So real quick, hold on one second. Patrick, that one you were asking about before class, very similar to that. Cool? Yeah, Jake.
So for this one, you definitely don't want to, unit vector notation.
You could leave it in unit vector notation. Keep forgetting what we decided. I need to be more specific. I think that we said this unless I said otherwise, right?
I think it was whatever is given in you answering that.
I'll be honest, if I'm not specific, I'll accept either one. Cool. I mean, you guys, by this point, you guys should be able to convert back and forth pretty fluidly anyway, right? All right, is everybody good with this? All right, part B is kind of the same, but there's a concepty difference that I want you to understand with part B. All right, so before I go on, are there questions about what we've done so far? All right. So part B, I'm going to cheat a little bit, and I know this sucks if you're taking notes, so I'll give you a second to get caught up. Get rid of this guy. Can I erase all the red and everything?
Yeah.
So, blowing up today. Okay, so part B says, suppose instead of part A, Carl is told that he's got 2 seconds to get the box moving at a constant velocity of 5 meters a second at 60 degrees south of east. What should he do? So he's got 2 seconds to push this thing, and at the end of those 2 seconds, he's got to have it going at 5 meters a second at 60 degrees south of east, and then he needs to keep it constant. Okay? So to answer this, it's sort of 2 problems in one, right? Because the first thing is, what does he have to do to get it to accelerate from rest up to this rate in 2 seconds, right? And then the second part is saying, then once he's accomplished that, what does he have to do to keep the velocity constant? Make sense? Okay, so we've still got the same force of A, the same force of B. Our net force is going to be different. All right, so why don't you're probably going to want to write this, I don't know, either write this out again or, just write yourself a note that same givens or something. I'll give you a second to do that. I'm not going to be quite as detailed with my calculations because once you sort of find out what your net force is, And then it's that same thing of subtracting your vectors and doing what we just did. Does that make sense? Anybody need another second? I see a few people writing. I'll give them a second. I try to leave some blank space on the page, you guys. Sometimes you might need an extra page to insert those, so I apologize if you're on tight on room. All right, everybody set? Anybody need a minute? All right, so for part B, there are two chunks. To get it moving, here's what we know. What was the initial velocity of the box? 0. Our goal is that we've got 2 seconds to get to a velocity of 5.00 meters a second at 60 degrees south of east. So what should I do? We can find the acceleration, right? We've got an initial velocity, a final velocity, and a time, right? So acceleration is v minus v naught over t. So you're just going to get 5 minus 0 divided by 2, right? So you're going to end up getting 2.5 meters per second squared at what direction? Same direction, right? If you want it to go that way, then you need to accelerate it that way, right? So we're still at 60 degrees south of east. Follow? So now that I've got my acceleration, now what should I do? Calculate net force. Yeah, now it's the exact same as A. All right? So I'm gonna kind of cheat here. Then proceed EDE, EED. Is it? I'm actually usually a really good speller. That's embarrassing. Okay. All right, and what you discover is the force of Carl here is, it ends up being, it's not quite due north, it's like a scotch to the west. It turns out to be like 89.4 degrees west of north, or like 0.6 degrees west of north. So I just put due north, so 90.71 newtons north. It's so close to due north that. Cool? Right, so what this will accomplish is it'll give it this acceleration. If he pushes for 2 seconds, it'll get to that velocity. Good? Oh, darn it. Oh, that black line is going with us. Oh, too small. All right. So then part C, oh, not part C. So then, to keep it moving, then what do we want to do? Good. We want to make the net force 0, right? To keep the velocity constant, right? So for 2 seconds, he needs to exert all of this force to cause it to accelerate to get it to the velocity we want. And then at the end of those 2 seconds, he's got to change his force to make the net force 0. So again, now we know our net force. So again, you proceed as an A. And you find that now the force of Carl, Walking Dead has forever ruined that name for me. Carl. So you end up getting 15.5 newtons at, and it turns out to be weirdly 78.0 degrees north of west. Even though it's moving, which way is the box moving? Southeast, right? So remember, just because he's pushing in a direction doesn't mean it's moving in that direction. Say it again. That's what I was hoping. Yeah, what do you got?
It's balancing the forces.
Exactly. Does that make sense, you guys? Good, you guys? That's about as hard as they get. I don't think there's anything even that hard on your homework. Okay? Questions? All right, so worksheet 5.1 is due Thursday. Okay, tomorrow the notes are really short. We're going to do gravity, normal force. There's not a whole lot to it. 5.3 is the big chunk of this, all right? So there you go. All right, did everybody, I know there were a couple people who weren't here yesterday. I need to get you guys your labs. Was everybody able to find the file that I shared with them, the comments? All right. Okay, good. I was going to ask how you guys like that. So your privacy settings on it are, you can comment on it. You can't edit it, because I want to be able to keep the comments that I had. But if you want, there's no reason why you can't put comments in there and mark it up yourself. And I think that's how I'm going to start grading the labs, and I hope that works. And then again, if you felt like I was unfair, you feel like you have questions or whatever, please talk to me, all right? At this point, I said to you guys yesterday we have to do a lab this chapter. I lied. It's actually chapter 6 where we're going to do a lab. So we've got a little time. So if you guys want more time beyond next Friday, I'm cool with that, all right? As long as you guys are working towards getting it done. Okay? Yes.
We can finish it and get it all set before the class.
A couple people asked, yeah, Philip asked me the same thing. A couple people said, if I can get it done by the end of the card marking, will you count it for me? Let me see if Pinnacle will let me do that. I think it will. I think all I got to do is just mark the assignment as no count for the people who don't turn it in, and then just duplicate the assignment next term and mark it no count for people who already turned it in. So if you did okay on it, have minor changes to make, and want to turn it in this term, that's fine. Okay.
When should we find out about how we're doing the test?
Trying to figure out the best way to do this. I mean, they're done. I just need to show them to you, but the problem is there's still a few people who have to take it, so I can't sort of pass them back. I also haven't figured out what I'm going to do curve-wise. I do think I'm going to put a curve on it again. Oh, and here's why. So tell me if you guys, I felt like the test was fair, but I think a lot of you guys ran tight on time. Was that? Okay. So like I said, I'm still trying to kind of wrap my head around how much time to give you guys. You know what I'd love to do is do every test like we did that first one, where there's a multiple choice part and a short answer part. But I don't think we have time, because if we do 15 chapters, that's 30 days right there, you know? So I don't know, I'm still monkeying with it, trying to figure out the best way to do it. So anyway, because of that, I think I'm going to curve it. I apologize about the mistake on number 7 that we realized at the end of the hour. So I keep making mistakes. There were 2 mistakes on that test that were highlighting resume mistakes. Now, to be fair, I should have done the answer key first. But I read the problem and I was like, oh, I know how to do that. I just foolishly assumed that the textbook would have the right answers, and they didn't either. So I apologize. So anyway, I am still working on it. So I'll tell you, I will share your grades with you tomorrow. Cool? I'll answer your question. All right, what I'll probably do is I'll call you guys up in small groups, just like 4 or 5 of you can come up with your test, and then, cool? Because I don't think the notes will take all hour tomorrow. Good? All right, are we doing okay, you guys? I have nightmares about this class. Really. Like, it stresses me out a lot, because I worry about all the mistakes I'm making, and I hope you guys know how hard I'm trying. Okay. Nightmares is exaggerating, but I do stress about it. All right.
Walking the floor, keep going, sliding out the door.
You gotta do better hiding the ducks, buddy.
What?
You gotta do better hiding the ducks you just left on your desk. What? Do what?
I thought no, you walked in and it was sitting on the side.
What? Oh. Yeah. Yeah. Sure. Yeah.
Number 12.
Yeah, thank you. Fourth one is literally pointing at Yes, what is that representing? Is that right? Very good. Oh, the next time, yeah. Does it say 8 here? Oh, 9. Oh, gotcha. Let's see, 2 forces. I'm worried you're finding the angle of the next one, that's not what you're looking for. Really, the angle of that two is that one. You found the angle out of that. So, that made it off. Up one goes this way, right? Up 2 goes this way, and then the horizontal component of 5. I don't think you want to here, so if you bring it this angle, we want this angle. Right.
David!
Whoa. Everybody okay? So your F1 points this way. Your F2 points this way. This guy over here is a nice horse. So your math, all of your intuition was right, you just got wrong. Good? Left, yes. Who else wasn't here yesterday? Beats are loud. No. I had it out this morning and I thought, I need to put this somewhere smart so that when they ask me, I'll know where it is. The question is, where did I put it? Wait a minute. So I told people yesterday was if you landed anywhere in the 70s, you were in the right. Okay. So you were in the 70s. That was one of them. Like one of them, I don't remember the exact word for that. So really, yeah. And also, towards the end, so I apologize. Did you guys look here or share the Google Doc with you? So the chat comments. So like you thought, okay, so those are corresponding to letters on your mark. Cool? Good? So if you want, totally, yeah. Now, if you want to go back to the corrections and get those points on correct, or actually get more, so it's really worth more than this point. So you get like, you know what I mean? I think it's worth under 5. If you're in I forgot to record him yesterday, but here's all we did. I'm scared with in here will be like, oh, I know that, I know that, I know that. So, yeah.
So awesome.